This lesson will cover graphing quadratic functions in vertex form. Before we graph any type of function, it's always nice to know what type of shape we expect when we graph it. In the case of a quadratic, we expect to get what is called a parabola. Now there's some defining features of a parabola that we need to understand. Right here is an example of a parabola. Four of the pieces of information that we need to talk about in regards to a parabola is number one, x-intercepts. X-intercepts are the locations at which your graph intercepts the x-axis. In our case, we have 1, 2 x-intercepts. Now, we could also have a case in which maybe our parabola comes down, barely touches the x-axis, and then goes back up. In that case, we would say we only have one x-intercept. It would be that bottom turnaround point touching the x-axis. And we could think of yet another example where the turnaround happens before we even reach the x-axis. So going back up to the statement here, this is why we say there are 1, 2, or 3 or 0, 1, or 2 x-intercepts. The next thing we need to talk about is the y-intercept, also known as the initial value. The y-intercept is the location at which our graph crosses the y-axis. For us, that's down at -3. Now, because the domain of a quadratic is all real numbers, meaning it travels forever in the positive x direction and forever in the negative x direction, we know that at some point our graph will always cross the y-intercept, but only once. So there is always one y-intercept. The next thing that we need to talk about, which is in many cases one of the most important pieces of a quadratic, is what's called the vertex. Now the vertex is either the maximum or minimum point on our graph. Otherwise, it can be viewed as the turnaround point. For instance, looking from left to right, our graph is decreasing, decreasing, decreasing until we get to this turnaround point, which we call our vertex, at which time it starts increasing. So it turns around from decreasing to increasing. That point is called the vertex. The last and fourth piece that we need to talk about is the axis of symmetry. The axis of symmetry is the vertical line that intersects the vertex and splits the graph into two halves that mirror each other. Parabolas are symmetric. The line of symmetry is that line that goes through our vertex, and as you can see, splits our parabola in half perfectly, each side a mirror image of the other. We would say that our parabola has symmetry about our line of symmetry. The equation of the line of symmetry, being a vertical line, we know it's x equals whatever location our axis of symmetry is going through the x-axis, in this case 1. So we could say that our axis of symmetry is the equation x equals 1. Now the example that we've been looking at, the parabola opens up, when in fact parabolas could open up or down. So this figure over here illustrates the two different scenarios of the parabola opening up in this case and the parabola opening down in this case. Now we're working with the vertex form of a quadratic function, not standard form. So vertex form here is y equals a times x minus h squared plus k. So we're going to be looking at quadratics that are in that form, where x and y are the variables, a, h, and k are constants specific to whatever quadratic function we're working with. Now this value of a is the value that tells us whether we open up or down. If the value of a right here is positive, meaning a is greater than 0, our parabola opens up. What does that mean about our vertex? It means that our vertex is the minimum value on our graph. Conversely, this value of A, if it is less than 0, in other words negative, our parabola opens down. What does that say about our vertex? It says that our vertex is the maximum point. In both cases, A being greater than or less than 0, the vertex is the turnaround point. But in the case of A being greater than 0, our vertex is a minimum. In the case of A being less than 0, our vertex is a maximum. So we have an idea now of what our graph of a quadratic, what the graph of a quadratic function should look like. Should look like a parabola, exhibits symmetry. It should open up or down. It either has 0, 1, or 2 x-intercepts, and the vertex is our turnaround point. So let's go ahead and start talking a little bit more about the logistics of how we graph a quadratic function. Graphing a quadratic function starts with the vertex. When in vertex form, which we have seen as y equals a times x minus h squared plus k, the vertex of a quadratic function is the point hk. So the values of h and k give us the x and y coordinates of our vertex. So simply by inspection, we can look at a quadratic function in vertex form, and the two numbers in those locations serve as our x and y coordinate of our vertex. Now the one piece to be careful with is this value of h right here, because you'll notice that in here it's x minus h, yet in our vertex formula it says h. So for instance, if it said x minus 4, the number we would pull out would not be negative 4, it would just be positive 4, because we're ignoring the negative when we bring it out. Now the steps to graphing a quadratic function are the same whether you're in standard or vertex form. We're going to start by, number 1, calculating the coordinates of the vertex. In this case, it's just hk, and then plotting the coordinates on plotting this point on the coordinate plane. Next, we're going to construct a t-table around the vertex and evaluate each x value selected in your t-table. These two are best described through some examples, which we'll get to. Number 4, we're going to plot those coordinates calculated in our t-table on the coordinate plane. Once we do that, we have several points, so step number 5, we know that we can now connect the points on the coordinate plane in the shape of a parabola. Lastly is just making sure we communicate information appropriately. Number 6 says we need to label the vertex and 2 additional points. And number 7, we need to draw and label the axis of symmetry. This just allows the viewer of your work to have a little more information and detail about the important pieces of your parabola. So at this point, let's move on to some examples to see how this process works. We've got our first example here. We want to graph the following quadratic function using the described steps above. So the quadratic we have to work with is y equals negative 1/2 times x plus 2 squared minus 1. Now again, we know that we always start with finding the vertex. Now what's nice is that since we are in vertex form, again reminding us of that, that's y equals a times x minus h squared plus k. Okay, we're in that form, our a being the negative 1/2, our h being, in this case, believe it or not, negative 2, because I'd have to plug a negative 2 in for h for the minus negative to give me the positive that I have right here. And last but not least, k is negative 1. So again, the tricky piece here is to understand that the h value is actually the opposite of whatever sign is in front of that h. So in our case, our h value is equal to negative 2, and our k value is equal to negative 1. this gives us the vertex coordinate point of -2, -1. Okay? Reminding us that h is the x coordinate and k is the y coordinate of our vertex. So we have our vertex now -2, -1. So I'm going to graph that. -2, -1 is the point right here. So we have our vertex now. Step 2 said, once we have our vertex, we want to build a t-table around our vertex. So to do that, I'm going to construct my xy t-table here. And in the middle of my t-table is where I'm going to put my vertex of -2, -1. Now again, because we want to see both sides of our parabola, I want to pick x values on either side of my vertex. So -2, I'm going to pick -1 and 0 as x values on one side of my vertex, and -3, -4 on the other side of my vertex. This will give me points to plot on my coordinate plane on both sides of my vertex so that I can see both sides operating on my graph. So what we want to do at this point is we want to plug the x values that we have chosen into our function and solve. Now just to keep myself straight, I like to put a dashed line right here so that I can do the work to the right of that line and then record the result in the y column. So here's how I'm going to approach this. We're first going to start with the x value of 0. I need to plug 0 into my function above and solve for y. So plugging in 0 for x, that gives me -1/2 times 0 plus 2 squared minus 1. -1/2 times 0 plus 2 squared minus 1. And what does this equal? Well, let's bring up our calculator. Okay. And here's how I'm going to enter it into my calculator. I'm going to enter -1 divided by 2 in parentheses, multiplied by 0 plus 2, close parenthesis, squared. So that's -1/2 times 0 plus 2 squared minus 1. Hit enter, and that produces a value of -3. So when I plug in 0, it gives me a value of -3. Okay. Now we need to plug in the value of -1. Okay. Plugging in the value of -1 produces -1/2 times -1 plus 2 squared minus 1. This was -3. So now we have a -1 in the location of our x instead of a 0. So again, we're working on -1 here. Bringing our calculator back. How am I going to enter this in? I'm going to enter it in as -1 divided by 2 in parentheses times -1 plus 2, and that is squared, and then from that minus 1. And when I hit enter, I get -1.5. So this is equal to -1.5. So when I plug in -1, I get -1.5, 1.5. Now we could continue this for the -3 and the -4, but because we know that parabolas are symmetric, we can figure out the values of the -3 and the -4 based off of symmetry. Because -1 is 1 unit away from our vertex at -2, and -3 here is also 1 unit away, we know that by symmetry, if I plug -3 in, I should get the same value as if I plug -1 in. So because of symmetry, I know that if I plug in -3, I end up with -1.5. The same argument can be made with the 0 and the -4. each of these values are 2 units away from your vertex of -2, the x-coordinate of your vertex -2. Therefore, their y values should also be the same. So because we got -3 when we plug 0 in, when we plug -4 in, we're also going to get -3. So you can even see the symmetry in our y column right here, because parabolas exhibit symmetry around the vertex. So now we have several points that we can plot on our graph. 0, -3 is this point here. We now have -1, -1.5. We already have our -2, -1 plotted. We have -3, -1.5. And lastly, we have -4, -3. Those points line up nicely in the shape of what we expect, a parabola. So what we can now do is connect these dots in the shape of a parabola to finish our graph. And there we go. There's the parabola, the shape or the graph of our function y equals -1/2 times x plus 2 squared minus 1. Now there were a few things that we needed to do on the graph to communicate that we know where certain pieces are. The first thing is we needed to label the vertex, which was at -2, -1. I then get to pick any 2 other points to label as well. I'm going to pick this point right here, which is at 0, -3. And I'm also going to pick the point right above it, which is -1, -1.5. So I've got my vertex and 2 other points labeled. What I want to do next is draw and then label my axis of symmetry. We know the axis of symmetry goes right through the vertex and splits our parabola in half. Now a vertical line crosses through the x-axis. Therefore, the equation of a vertical line is x equals wherever it crosses through the x-axis. Crosses through the x-axis at -2 for us, so the equation of our axis of symmetry is x equals -2. We now have our parabola completed, the graph of our quadratic completed, with the vertex, 2 other points labeled, our axis of symmetry drawn and labeled. To further solidify this process, let's go ahead and do another example of graphing a quadratic in vertex form. Our next example is as follows. Y equals 2 times x plus 2 squared minus 4. So again, we always want to start with finding our vertex. In the case of a quadratic in vertex form, we know that our vertex is the point HK. Now again, reminding ourselves that vertex form is y equals a times x minus h squared plus k. Again, reminding ourselves that when we extract the h value from our quadratic we're working with, we need to think opposite in terms of sign. So in reality, our h value here is equal to -2. Again, because there's a negative in front of the h in the vertex form. So in order to get a positive number, as we do here in our example of x plus 2, h has to be a negative. And then our k value is just the value in that last location right here, the constant added to the end. In this case, it's -4. So you think opposite with the h, but you don't think opposite with the k. So the h is our x coordinate, so -2, and k is our y coordinate, -4. So -2, -4 is the location of our vertex. Plotting that, I get that right here. So here's the point, -2, -4. So now it's around that point that we construct our t-table. So we've got our xy t-table here. I'm going to move that over real quick. got our x, y, t table, and we're going to put our vertex right in the middle of that. -2, -4. And just like we did on the previous example, the goal is to pick 2 points at least smaller than and 2 points at least bigger than our vertex. So our x value being at -2, I'm going to pick -1 and 0, and I'm going to pick -3 and -4 on the other side. Okay, so separating my work right here from my table, I'm going to start with plugging in 0 to my x and solving for y. So plugging 0 in for my equation, that leaves me with 2 times 0 plus 2 squared minus 4. 2 times 0 plus 2 squared minus 4. So bringing up our calculator, that is going to be a 2 times 0 plus 2, close parenthesis, square that, minus 4. Hit enter, and I'm getting a positive 4. So this is equal to 4. So that means when I plug 0 in for x, I get a y value of 4. Now that I plugged 0 in, I'm going to go to my next x value that I selected and plug in -1. So that looks like 2 times -1 plus 2 squared minus 4, and that equals what? So bringing our calculator back, we end up with 2 times -1, oh, not -1, 2 times -1, let me clear that out, 2 times -1 plus 2 squared, and then minus 4. Produces a value of -2. So when we plug in -1, we get a y value of -2. Now again, because we chose the x values we did, we know we have symmetry. -1 and -3 are each 1 unit away from our vertex of -2. Therefore, I expect to get the same y values. So because I got -2 when I plugged in -1, I know I get -2 for my y value when I plug in -3. Likewise, because the x value of 0 and -4 are both 2 units away, just on opposite sides, we know by symmetry that we expect the same y value for both. So because we got 4 when we plugged in 0 for x, we know we get 4 when we plug -4 in for x as well. So we now have several points that we can plot on our coordinate plane. 0, 4, 0, 4, -1, -2. We already have our vertex of -2, -4. We have -3, -2. And -4, 4, which is up here. This parabola is much thinner than the previous one, but it still lines up very nicely in the shape of a parabola. So we're going to connect these dots to give us the parabola that we were looking for. And there's the graph of the quadratic function y equals 2 times x plus 2 squared minus 4. Let's label some things to communicate we know where specific things are. Labeling our vertex, -2, -4. That's done. We want to label 2 other points now. I'm going to pick the 2 points to the left. So that would be a -3, -2 here. That's that point. And then this point way up here would be a -4, 4. So I've got my vertex and 2 additional points labeled. I now want to draw my line of symmetry, which goes, it's a vertical line straight through my x, or straight through my vertex. And we want to label this. It's a vertical line, so we know that the graph of a vertical line is x equals wherever it goes through the x-axis. In this case, -2. So x equals -2 is the equation of my vertical line, the axis of symmetry.